Hello, everyone. It's such a great pleasure to be here. So I want to say, Adwi, thank you for inviting me. I mean, for those who are working in the natural language field, they know that if it wasn't for Adwi back in the day pushing to do machine learning for part of speech tagging, field was going to be very different. And also we were lucky and fortunate enough to have worked together at Yahoo, tackling both ads and search. So I'm super happy to see that Adwi is taking to the next level, training the next sets of NLP experts that will join industry. So Advait and everyone, nice to meet you and thank you for inviting me. So for those of you who don't know me, so I'm Zornitsa and currently I lead search efforts inside Google, trying to make sure that everything you're looking for inside your G Suite, that means mail, chat, as well as Drive and Docs, goes as smooth as possible. There's a lot of NLP going into making sure that we provide the best experience and technology. But today I want to focus on something that is very novel. So I lead also the on-device NLP efforts. And I'm going to talk about that because literally that's the future. And these are some of the things that people are trying to think about and how we can solve them. Let me start by explaining, okay, where is the motivation for that? So back in the day, one of the biggest challenges for all the folks in academia was the lack of data. And as data kept growing and resources kept growing, suddenly with deep learning, everyone is building big neural network models that live on the cloud. And that has become the norm. But over time, if you notice, we're carrying our mobile devices everywhere. We have smartwatches and a completely new trend has emerged. The trend is, can we build like tiny small neural networks that run entirely on your devices? And people would say like, well, why do we really need that? And here are like 4 core components. So when you work in industry, you have to also make sure that you consider user privacy. That's super important. All users really want to have the best features, but then they get very worried, like what happens to my data? Where is it stored? How is it obfuscated? And if you actually have models that live entirely on your device, they never leave your mobile phone, then you can preserve their user privacy. And that's why one needs to build such type of on-device models, that the data never leaves your mobile phone, your watch, your smart speaker. Sometimes we also have to worry about limited connectivity. Imagine you're driving with your car down the road, you pass in a tunnel and suddenly you lose connectivity, or you're going hiking and for example, you don't have access to fast speed internet, but you still want to use your fast functionality and voice control and say, remind me where's my next meeting, or remind me what's the phone of Adwait or whatever, right? And that can happen if you build on-device models. Third, very important aspect is like, can we take advantages of efficient computing? Now we have all kinds of chips that have been made to develop like powerful neural networks, but we can do exact same thing for efficient computing that will happen entirely on your mobile device. And last but not least is consistent user experience. So every time a user comes to our products, we want to make sure that whatever they type, they always get the same response. So that's how the whole motivation started. And to make sure that people are on the same page, I'm going to give you a lifetime example. Unfortunately, I cannot see everyone in the Zoom, but I tend to ask people, so how often do you use your assistive devices, whether it's your Google Home, your smartwatch, or your mobile phones? And most people use it minimum like 2 to 3 times per day. And for me, everything is voice control in my house. And even a basic command like turn on my living room light. Right now, what we do is we take this language and we send it to the cloud, where we do a couple of things. We extract the intent because we try to understand what the human is trying to tell the system. Like turning on is evoking a command that says, like bring light to happen. We extract entities like living room. We know that it's a location in your house. Light is the entity or the so-called device that we have to activate and to make it happen. But even if you use this command like 5 to 10 times a day, you're going to see that there's like a small lag between the time you request the command and the time the light turns on. And over time, it gets very frustrated because it's been 1 minute and your light might still not be turning on. So what does the user do? They open their phone and they just start directly turning on and off the light from their app. So that's not the experience we want, right? And the delays can happen for many reasons. It could be happening because of the processing on cloud. It could be because of the connectivity issues. There are all kinds of things that can lead to that experience. So this is where the solution is. If you build it on device, it means that you can smart control your light directly or your plug. It will happen in milliseconds and the experience will be much, much better. Fast forward, you can think that you can start plugging this kind of machine learning models for anything, for your smartphones, for your fridges, for your, for example, microwave, and just tell them, heat the food or execute any kind of command. Another example is smart messaging, right? For those of you who love smart reply, we can build same applications for your watch. You can just say like, hey, what's going on? And the machine learning model can automatically predict, I'm doing good, I'm doing great, thumbs up, and you can just like self-select. You don't even have to do any writing or typing or swiping. So this is the technology we want to build. We want to build small, efficient networks that reside on these devices and that can solve all kinds of endless applications that we use on a daily basis. So oftentimes people come and say, hey, this is a great idea, but I don't see what the challenges are. And the answer is that there's endless challenges. Like if we look, we have lots of hardware constraints, unlike cloud, where you have unlimited memory, unlimited computation. Here on small mobile device, you have to fit something in kilobytes. So you have super small memory space. You have to make sure that the models that you're building, they shouldn't drain the battery of your mobile phone. And we always want them to have the same good performance, just like the server-side applications, which is extremely, extremely hard. For many years, people tried it and they literally failed. We want to be able to run complex architectures, and we want to do different tasks like structured predictions, which are typical things like extracting entities, extracting relations, doing question answering over data. We want to be able to handle like high dimensionality data as well as like large output spaces. What's a good example? Let's say you pass an image, you want it to be classified into 40 million classes because that's what we're doing on cloud applications. So we want to be able to support the same things with the small memory chips and devices. So before I share like what we have designed and how far we have reached, I want to kind of show like where people were all the way until recently. So people say, well, that's easy problem. All you have to do is you take the input and the output, you hash them, and hash lookups are super fast, super efficient. This problem is solved, it's not a problem. But these people are not experts in language processing because objectively speaking, language is very ambiguous. There's high diversity. And even if you just decide to do this example for something like musician, and you say like, I want to say play songs by someone like by Madonna, very quickly you're going to see that the vocabulary of how you can say play a song is very large. And later if you start trying to put all the musicians in the world, you would need to do like another dictionary lookup. And suddenly from something that seemed like such a small intuitive problem, you open up a can of worms and you see that that's actually not solvable. And this hash lookup is not gonna get us anywhere. So in 2012 and 2013, a couple of people started picking and saying like, well, maybe we can do some smart sampling. Maybe we can also add some graph algorithms to try to solve this problem. And the answer is like, yes, to some extent, but the problem is they end up with such bulky models that you cannot actually fit them on the device, or you can just fit some small subset of examples or domains. And that's not how real world actually works. So then Sujit, who is a colleague of mine at Google, now he moved to Amazon where he's leading Amazon Alexa. Both of us were sitting and we were asking each other, okay, well, can we do actually better? We know that deep learning is like trailblazing. We know that it's reaching state of the art. Well, can we actually take these neural networks and fit them on small devices, make sure that they're small inside, make sure that they're very efficient, and at the same time get some near the state-of-the-art performance. And most people to whom we share this idea, they all said like, well, no, that's not going to work out. And here's the good news, actually it does work out. And we introduced like a paradigm of how these neural networks actually can be built on a brand new family of so-called projection model architectures. And here's how it's working. Literally we made it like a plug and play model. You come up with your data for whatever problem you have. So X is your data and you tell us what's your desired output, like Y. This could be like specific label classes that we're trying to predict, whether something is hate speech or not, whether something is specific category or not. And what we do is like we take your data and we take your labeled examples and we ship them on cloud, just like any other method. And we train specific types of projection models that we propose, which produce very efficient and customizable small neural networks. And I'm gonna show you like three different variations of these networks and how far we've gone together. And the good part is like once this neural network is trained, we produce like a TensorFlow Lite, which is a special library made for like edge devices such as phones and watches. And you just take that model and plug it directly for inference on the device. So all the inference happens on the device. The good part about these networks is that people can come and can say, hey, I have this requirement for such size models. We want to be that fast or that slow. And we support and customize all of that. So all of these things are super customizable. All of them run on TensorFlow Lite. So here's the first neural network that we introduced. We call it a self-governing neural network. Typically, like any NLP application, like your input is some kind of text. In our case, we were first interested in short text. So even if you have something as simple as like the quick brown fox jumps, the first thing that we do is like we extract features. This is what any NLP task does. It could be like simple things like n-grams and skip-gram features of different lengths, or you can make them as complex as you want. But one of the things that we definitely don't do is like word embeddings, which is like what all of the current neural networks are using. They're using either pre-trained embeddings or the problem is that they're so huge that even if you just try to preload them, it will take 5 gigabytes of memory, which is something that you don't have. So that's why we get rid completely of embeddings and we try to learn so-called projection representations or projection on the fly. And the good part is like we take a text, for that text, we quickly extract the features. And the next thing that we do is like we hash them into specific like sparse vectors. So you can think about the feature that you want, like the quick brown fox, you map it through a hashing function, the string into like an integer, and you have a weight, and the weight is typically how frequently did you see that specific feature in the text. When you work with short text, most of those features are just ones, but if you work with little longer text, you're gonna have like different counts, how many times you saw this feature. This is very standard, nothing special about it. But where the magic comes is into the so-called projection layer. This is all the magic where you have these very, very sparse vectors that actually sit down and get compressed into binary projection vectors. And these binary projection vectors has two properties. One is like T, which is the so-called functions that we want to map into the hashing functions, and G is the dimensions. And literally we use locality sensitive hashing, which is very frequently used actually if you do dimensionality reduction to compress these large vectors into small compact vectors. To do that, we start with like a random seed vector, and when you multiply the random seed vector by the sparse vector for each of these like T hashing functions, you end up with these projected vectors that is binary of zeros and one. Typically, if you take these two sparse vectors like the random seed and the current random seed vector and you do the cosine, if the two are very close to each other, then we'll know that they'll be in the projected space very similar to each other. Otherwise, they'll be very, very far apart. So there's a super nice talk from Sujit about the details and all the proofs happening behind the projection nets. It's at ICML. I encourage you to look deeper, but literally that's the magic that allows us to operate from these very, very high dimensional spaces into small compact spaces of bit vectors that are super fast, super efficient, allow us to get rid of all the embeddings and allow us to build these small compact models. And as I was saying, is like when you take sparse vector and you compress it with LSH, what ends up is like you have semantically similar phrases that are super close next to each other. And that's exactly like what we want. So once you're ready with the projection vector, the next thing what we do is like just like fully connected layer, and in the end we just do softmax on top. Main reason is because we do a lot of these like multi-class classification problems. And for us, it was like a big revelation. 2018, first time somebody showing that, hey, you can do these like super efficient on-device neural network models. all the computation is happening on the fly, given text input, all the features are extracted on the fly. We don't store anything. We don't like pre-compute anything. Super lightweight, super fast. And that also allowed us to do like these super small representations. And as you see, like end up with like small compact models that are very, very efficient. Now the question was, okay, now that we have some network and we know that it is possible to build it and train it and make it small and efficient, how well does it do? So we decided to test it on different types of tasks and look at the complexity of those tasks and where is it working, why is it working. So we started with the switchboard dialog task classification. And the idea is like you have two people, they're talking to each other, and every time a person says something, we need to predict one of the 42 dialog acts. So somebody says about 12 foot in diameter, we say it's a statement. Somebody replies to that, oh yeah, we know it's a back channel. Do you ever think about that? It's a yes, no questions and so on. So these inputs come one at a time, and we literally predict like, what is the person trying to say? You can think that in real case scenario, exactly those statements that we are predicting or those labels, they're the same as the intents that people predict when you do like a real-time assistant task, like turn on the light or turn off, for example, the light and so on. The good part is like we decided to use open data sets such that people can easily compare. And at the same time, we wanted to see like what happens with our own device compared to all the existing neural network models. And there's plenty of work that, that has been done in this area. So if we start with the traditional HMM approaches, you're going to see that our model actually is lightweight and it's also improving on top of that. But also most interesting is that it's improving compared to all the RNN gated attention model that people have started trying over the past years. And the interesting part is like those models are actually much more bulkier and have many more parameters compared to the SGNN model that we have proposed. Then we decided, okay, well, maybe the task was simpler. Let's keep increasing the complexity. Now, what happens if I give like a multi-party conversational data? And now I have...
Sorry, can I ask a question, like a clarification question? So in the, this SGG or SGNN network,
Yep.
so so is my understanding correct that it, you know, you project to these input features and then you basically train a network on it, or do you back propagate, like when you're doing the learning, do you update the projections, or are
yes,
they...
you update all the way to the projections, correct.
And but you also learn the projections during learning, is
correct?
That...
Yes.
Cool. Okay.
Yes, correct. And in this current complexity of the task, as I say, now we have multi-party. So we have more than two people talking to each other. That means that the language variability should be higher. Some people speak a little more than others. So the task is still the same. You have multiple people, different variety of the length of the text, and we still have to predict the same type of dialogue acts. So here's like some example of how that looks like. And the nice part is like the same people who actually evaluated on the previous data set, they were also having models for the same models actually for this task. One thing that they were doing that we were not doing for sure is they were fine tuning the parameters of the networks over and over again. In our case, we use exact same parameters for both tasks. And one of our reasons is like if you build a real application and you have to put it on your mobile phone, you want to make sure that you have one universal model that can actually do multiple tasks. So you don't want to have like hanging 5-6 different models, right? And one of the things that we see is that even in this task, like the performance kept increasing and we were doing much better than the CNNs and RNNs. But we got like very close performance to one of the authors on the RNN, and we actually dig deeper to understand like what happened. We got in touch with them to understand. And one of the things that they said is that they use a lot of like pre-trained data. They actually pre-trained on additional dialogue data that they have found. In our case, we didn't do that. We just use the data that we currently have. But if we look at the two models, like the RNN has millions of parameters, while the SGNN has like very, very small, like compact model, just 300K, which is like super impressive in getting that type of performance. So we got super excited, both people internally in the company, externally, everyone was like, okay, great, first neural nets that are working on, let's say, mobile devices, super small, super compact. Then we started asking ourselves, okay, is there something that we can do? Can we do the models to be more efficient? Can we take some advantage from, let's say, the structure of the language? And that's how we did the next version, which is called SGNN++. And here's like some high-level details of what that network actually is doing. So in the previous example, we were just taking the input and we were generating mostly like word representations, yes. But we do know that characters actually give a lot of information in language, right? We have morphologically rich languages. So if you're trying to do these kind of models across, let's say 20 to 100 languages, morphology is super important. We wanted to have a model that can learn both like word representation as well as character representation, have both of them projected. So if you see on the left side, this is the word portion of the model, and on the right side, we have the character portion of the model. Each of them are learning projection representation. And in the end, we concatenate those two representations. So this is the so-called joint structure projection. But at the same time, we have something that is called the context partition projection. So what that means is like in the previous case, every time when we generate features, whether they're unigrams, bigrams, trigrams, or skipgrams of that length, we always used to reserve the exact same bits, vector bit spaces, right? And though this is good, actually, sometimes you can have collision between the n-grams. So what we decided to do is like in this current version, we reserve specific sets of bits for different, let's say, level of information. Unigrams have specific bits, bigrams have trigrams, fivegrams, and so on and so forth. That lets us avoid the collision. And number two is like, it's much easier in terms of implementation and lookup. And also when you have to compute the bit vectors between, for example, a 5-gram and the projection vector, it will be much faster if the vector space is smaller compared to, let's say, before when we used to reserve equal space across all the n-grams. And also over time, one thing that we learned is like, if you partition this space for the words and characters and kind of try to concatenate them together at the end, and if you do this kind of like preservation for how many bits go for each of these like n-gram submodels or sublattices, that actually leads to magnitudes of higher performance. And here's some example. We use exact same MRDA and SWDA data sets for dialog. And we have comparison, again, our previous model, the SGNN. And as you see, performance actually does improve significantly. And people should ask the natural question. So where is the performance and improvement coming from, or why? And I'll show later like how we study that in detail. So we do a little bit of analysis, but at the same time, I want to show like additional tasks. We kept adding tasks and we kept adding languages. So it gets very interesting to see how these models actually generalize across all of them. So we added another one, which is a very popular 80s intent prediction data set. It's like mostly for flights, for people who are trying to talk to a dialog agent and say like, how far is Auckland airport from downtown? It understands that the intent is like you're requesting some kind of distance. Or if you say what's the price of a ticket from LAX to SFO, it is asking for airfare and so on and so forth. Like these are real case scenarios that are very practical and useful. Even if we start comparing to that, let's say majority class baseline, where you just predict what's the most frequent class in the data set, we're actually improving over that. And we notice that we're also improving over current models that are trying to do joint entity and slot extraction. What does it mean? That if you know that SFO is an airport and LAX is an airport, and you extract those entities and pass them as a label to the model, your intent predictor can become much more accurate and tell you like, well, you're looking for airfare or you're looking for a flight destination. So it turns out that our current SGNN++ actually does even better than such type of models. It achieves the best performance. But as I said, like our motivation here was not only to expand the number of tasks, but also we wanted to see languages. So how does this model do in terms of like, let's say English, Japanese, French, and Spanish? And one of the things we noticed, like it's super hard to get similar data, let's say across multiple languages with the same type of annotations, such that you can actually compare and dive deeper. So we did find people who created a lot of of customer feedback data set. Literally every single sentence or utterance that somebody was talking to an operator and either filing a complaint or commenting or bugging or requesting something was annotated consistently across all of these like 4 languages. So we're very thankful for them to sharing that data set with us. And we decided to compare our performance with all of the different models that exist out there. So the similarity baseline was like the simplest model, which given a sentence, it's trying to measure the trigrams of, let's say, from every sentence you extract trigrams and you just measure similarity between 2 sentences via cosine and try to see like, oh, if I have the current sentence and I don't know the label, but here are 3 sentences that are very similar, then likely the label of the current one should be one of these 3 that are most similar to it. Over time, people have actually done a lot of like pre-trained embeddings, injected a lot of sentiment information to capture things like complaints, added external knowledge bases. But if you see, in our case, we actually abstract from this information and still consistently are doing very well across all the 4 languages. One model that we couldn't outperform was the Planck model, and a couple of interesting things is like actually Barbara Planck, she used like a translation model to take all the data from the different languages, translate it to create like larger corpus. Then she used a lot of multilingual embeddings that she had on the web, as well as like part of speech tagging information. And technically one can keep incorporating and making all of those models more complex, but there's one challenge. If we do this on the cloud, definitely that's the way to go. But if you do it on device, if I want to use like a part of speech tagger, that means that I have to have another model that has to run in parallel, which might not always be possible. As I said, like it's very hard to load embeddings. Even if you just take the Word2Vec embeddings, they're 5 gigabytes. They won't fit on your mobile phone or they won't fit even on your mobile watch. So these are not practical applications. But the good part, what we are super happy about is consistently we use the same parameter settings for all of these languages and all of these tasks, and they're getting very, very good and robust performance consistently across all of them. And in the current version, as I said, SGNN++ captures very well like some of the morphological characteristics which help for languages like French and Spanish. So now, as I say, like what's interesting to understand about SGNN is like what happens when we use this partitioned projection, as well as like what happens if you just use words versus if you use words and characters. And here's like a couple of comparisons that we did that help answer these questions, ablation studies that people can actually just use and rely on. So for example, consistently, if you look SGNN, whether you do partition or non-partition representations, if you use actually words and characters compared to words, actually this is always much better. That means that characters give you this extra boost to capture something about the structure of the words that is very important when you try to do this type of text classification. So for example, if you were doing the partitioning, you see that the word plus character is better. Even if you don't want to do the partitioning of the space, which means reserve the specific bits for your projections, even there, like word characters are doing much better. When we do different type of experiments, we want to know like, okay, so should one actually sit down and implement partitioning versus non-partitioning? You can see that partitioning works much better. That means that if you take in specific n-grams, you reserve space inside the projected space. That's way better than if you don't do that. And that happens both for word and character, or even if you just like take the words themselves and you don't want to add characters to your model. But the high level takeaway message is that actually, if you do projections, partition projection plus word and character, that gives you like the best representations possible. And you get like over 10% improvement per tasks. And that's like actually the way to go. And that's that's how we actually kept evolving our models, like as we kept developing these networks and keep solving challenging tasks. Something that's super important when we build these models is, as I say, the model size, right? We are trying to do 2 things, which is accuracy. We want to make sure that they're as accurate as server-side application, but also at the same time, we are trying to keep them as small as possible. And if you remember, I started the slide saying that our architecture allows you to customize super easily. based on what the person's needs are. Here in this graph, and I'm not sure if my pointer is showing, but on the y-axis you have the accuracy at precision 1, and then on the x-axis you have the size of the TensorFlow model. So if you see, we have different types of projection functions, like a T, which was like how many functions do we actually want, and G is the dimensions that we have to reserve for those functions. So when you multiply the two together, you get the dimensionalities like we're working with. And if you see that you can have very high accuracy, like 94.7, and you can just produce as small as like 2.5 megabit model, which is like super, super impressive. The good part is like these models are super customizable. Like if you see, we can do even like smaller models like 0.4 megabit, which goes to 86 performance accuracy, or you can even drop down to like 100 kilobyte models with 82% accuracy, which is super, super impressive. I mean, that tells you that literally instead of running stuff on cloud and shipping back the predictions to your devices, you can just run them directly on the device. But another thing that is very interesting is like, can you actually keep compressing those models even more? So if you see, there are this QOPA model. Q stands for quantization. So that means that if you have, let's say, a 64-bit model, we're trying to even compact it even more to make it like, to fit it into 8 bits. That means that the models get so tiny. Like you see 7 kilobyte model, this is like nothing, literally, like still having like 77% accuracy. And this is like super impressive. And that's like one of the, how do you say, the things that we showed and demonstrated and help people inside production actually realize the beauty of it and get more confident on using that for real-time prediction and for real use cases. So what's the good part about SGNN? As I say, they're really small, they're super highly accurate, and they're super fast. And one of the things that we do is that we always measure latency. So how do we do that? We take Pixel phones, which run a lot of the Android operating system, and we care about if I pass some input text, how much time would it take on this Pixel phone, for example, to do everything from the extraction of the features on the fly through the prediction of the models. And we did that on the full 80s dialog data set, and we averaged the time, like how much time did it actually get for us to run the whole data set on average, get the predictions, and have this high accuracy of like 93%. And the answer is around 3.3 milliseconds. This means it's like super instantaneous. And as I said, the most impressive part is like the models are super small and very, very fast. So that was so exciting. People were like, wow, amazing. We see now that you can do that for small short text, like think about it, your tweets, your messages, any of these like little cute short texts. But then people started asking us, well, how about if you do it for long documents? And unfortunately, when you run both SGNN and SGNN++ models, they don't do that great for long documents, right? So that required us to start thinking about different architectures that can actually capture better information. And we came up with the next model that is called like Prosecco. It stands for Projection Sequence Networks. And here's how it goes. It's similar to the previous models. You always start from the word, but now the representation is a little different. Now we learned that characters and morphology are very, very important to capture the properties of the text and to make these like on-device predictions highly accurate. You can also add syntax, but as I say, the challenges are that you need separate models, and then your inference time is like it's dropping down, which means it's not good for real-time prediction. But we also know that in language, when we do things on the cloud, everything depends on the context of the words. That's how many of the word-to-vec models are trained, BERT is trained. All of these models depend on the context of the words around them. So we decided to combine the best of both worlds. From one side, we keep our character morphological representations and their projections. But at the same time, if I take, let's say, the word, maybe this is better, the math is better. Like if I take the word W2, we operate with context windows of 2-3 words to the left and to the right, just like any other, let's say, word-to-vec representation would do the same thing. So what we do is like we concatenate the two together, the context projection as well as the character information, and we learn projections over those. Once you have your projected vectors, then we feed them in bidirectional LSTM, which is very standard. And to make sure that these networks actually start learning better, we try to make the networks a little bit deeper. So we kind of stack 2 layers on top of each other. The bidirectional LSTM, then we have the final layer, and we do the softmax output. So the good part about these specific networks is that they're fully dynamic, which means that unlike the previous ones, these ones actually capture the context around it. They're also like embedding free, memory free, and as I say, like they take also the recurrent operations into account. That allowed us, this kind of modified architecture allowed us actually to handle a much more complex task, including like how to model like longer documents compared to the previous SGNN and SGNN++. So here's some examples. We took all the different data sets that people in text classification truly like working with. So we divided them by short as well as like long text. If you see, like some of them have like 42 classes, some are like just 5 classes. The vocabulary is very different. Some have like very small vocabulary, like 1,000 words, but others like the Amazon product review has something like 2 million different words. The average length of the text is also very different. The training data, some have like 3 million training examples, and they have like 650,000 test examples. So we try to capture as diverse as possible, and evaluate like how are these models going to do compared to what currently people are doing. And here's some examples. In the short text, you kind of saw what SGNN, SGNN++ was doing. And if we take all of those approaches and we compare them to Prosecco, we actually see that Prosecco is doing magnitudes better, both in terms of improving state of the art, but also in terms of like, even if we just take their parameters and start comparing how much the difference between the 2 modules is and how small and compact they are. That motivated us to keep going forward. And even if we compare to our initial first version of SGNN, we see that actually the recurrent structure and the dynamic projections are much more robust compared to like what we were doing first in 2018. Then if you go and now start seeing like what's happening on the long text, one of the things that we did is like we took all the recent works of people who are doing the LSTM, CNNs, hierarchical attention, which are also very popular. Note that these models were not designed to run on devices, but they're very relevant, and it's good to compare just to know like, okay, can we get or can we improve their performances? So if you see, Prosecco actually gets very, very high performance. There here and there some models which we notice that they train for specific tasks. Let's say the hierarchical attention by Young and Smola. They focus a lot on the Amazon data, and they work great when you have larger text and larger training. But they didn't do like, for example, Yahoo Answers or some of the other tasks, right? In our case, consistently, independent of the length of the text, the vocabulary text, the model was doing like really, really well. And as you see, all of the models which are in the purple box, all of them use like pre-trained embeddings, and all of them have like huge parameters compared to ours. So when we compare on-device versus on-device models, if you see Prosecco against our own SGNN, if you recall, SGNN was taking all the, which means all the text in one shot and extract the features, right? In one shot, it just goes and does that. It has a very, very hard time actually capturing long-term dependencies and understanding what's happening in long text. So if you compare for AG News, which was the news articles, you pass a new article and you have to predict the category, Prosecco is doing way better. It has 91%. One is like that shows you that the recurrent information that is being taken into account and the context are very, very important for this type of tasks, and actually can capture like long-range dependencies compared to the SGNN. And that happens consistently for Yahoo Answers as well as like Amazon reviews, which is very impressive. And that's like the models that right now we are using. We actually have like an attention version for that as well. But these are kind of the models that we are using. And it's just amazing to see like how in 1 to 2 years, like these models can evolve and we can keep pushing and solving more and more complex tasks. Couple of things that it's nice to also think about is like, how much is the effect of the projection size, for example, on accuracy, because I told you, like, we work with such small vectors. So if you have the T by D, which is literally like our vector spaces, they're super small, like 300, 600, 800. And we just do the compression ratio of our model versus, for example, a very basic LSTM model that has like word embeddings, let's say 150,000 vocabulary size, and their embedding size is like 300, which are like the pretty standard, like word embedding models. And dimensions, you can see that our model Prosecco still keeps accuracy of 90%, but it has like a compression rate of 10,000 times, which is like super impressive. And our models are like 3 times, if not like more magnitudes, like smaller compared to all of those models. So this is super, super, I say, remarkable, especially if you do things in production. So some of the takeaway messages for Prosecco especially, it's like embeddings free, as I say, independent of what task, of the length of the text, whether it's short or long, what's your vocabulary size. As you remember, like we had even 2 million vocabulary sizes. Prosecco is always constant in terms of like our space, which is T by D. And its performance is consistent across the task and the data sets, which is like really, really good. And as I say, if we compare it to GloVe, word embeddings, or any of these models, you can see that the models we produce are like tiny, just kilobytes of storage compared to what the state-of-the-art models are doing. So moving towards conclusion, well, it's super awesome to see like where we started and where we are 2-3 years later. We truly laid the foundation for all the on-device neural networks. And actually over the past years, we organized multiple workshops at ICML, bringing together the community to solve this problem. So we have very close connections also with the vision community that is trying to solve these problems as well. Also tackling challenges and trying to reach to such performances. And it's super awesome to see that we have at least 3 different networks that we propose for language understanding tasks, and just kept improving the next version. And these models that we propose that are the projection-based methods are, I say, very compact, but somehow manage to capture the semantic representation and still get like good performances. The high level like blurb is that each of them kept improving the state of the art and pushing the boundaries. And I hope that more people will jump in and try to solve these problems. And one of the things we're currently like passionate about is like keep adding more languages, as well as we are doing a lot of tasks on structured prediction, which is even like a more complex problems. This is the question answering aspect, this is the information extraction aspect for them. So with that, what I'll do is like, I left like some links to recent papers, and also some of these talks are recorded. Like each of these papers has like a talk that's recorded at the conferences. So you can get more into the technical details there and see more detailed explanations. And with that, I would like to thank you. And if anyone has any questions, I'm happy to answer or point you to the right place where you can actually read more about it.